Hello student, good morning. I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I will continue from the last class. Last class I have started D and F block element. In that I have discussed about D block elements, and in that I have discussed first series of transition element, second series of transition element, third series of transition elements, and fourth series of transition elements. In that I have told you that I will tell the name of fourth series transition elements. Here name of elements are based on scientist's name, and their name is somewhat uncommon. Then its member starts with actinium 89, AC, symbol is AC. After that directly it is 104. Then 104, its name is Rutherfordium, RF, Rutherfordium, name of the scientist. Almost all names are based on discoverer name. Actually these are man-made element, also called transuran element. Question is asked. Then 104 is Rutherfordium, and 105 Db. Db means dubnium. It actually it has another name also, hanium, HAHNIUM, hanium, but popularly known as dubnium. Sometimes it is known as hanium also. And after that 106 SG, its name is Seaborgium, SEACBORGIUM, Seaborgium. And 107, it's a BH, symbol is BH. And Bohr scientist, you have Neil Bohr, on his name, borium, BOHRIUM, borium. 108 HS, that is called HS. Then that is called hassium, HASSIUM, hassium. And 109, its symbol is MT, and it is called meitnerium, MEITNERIUM, meitnerium. And 110, its symbol is WN, and its name is ununilium, again UNNI, ununilium. And it has another name also, that is the Darmstadtium, DARMS, TADTIUM, Darmstadtium. Okay, DARMS, 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 TADFITIUM, Darmstadtium. Okay, Darmstadtium. It is the name of scientist. Now another 111. Its name is triple U, symbol is UUU, and its name is, for one U, UN, for second U, again UN, and for third U, again UN, 3 times UN, 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 and in the end you add IUM. IUM. Everywhere you adding in the last IUM, same way here IUM you have to add. Okay, then UN, UN, unium, UN, UN, unium, and another name is Wrongton. You might have heard the name of scientist Wrongton. In his name, Wrongtanium is also called Wrongtanium. And 112 is UUB. Again, U means same, UN. Second U means again UN. And B means BM, means BM. BM. Then these are somewhat uncommon name, and generally in lower classes you will not use. These are the I can say elements which is used in higher level in nuclear reaction. Actually these elements are also called trans-uran elements, or also called man-made element. 103 onward, almost all are man-made element, trans-uran element. Okay, up to 103 it is a natural. You will find in nature. Okay, means inside the earth. Then this I have discussed about the name of the fourth series element, transition elements. Fourth series transition elements. Now only here I want to tell about the two series, lanthanide series and actinide series name I will tell. Okay, little details I will tell at the proper place. But now this lanthanide series and actinide series, this name of the elements I want to tell you. Okay, because these are again somewhat new for you people. Then this lanthanum is 58 to 71. 58 to 71. Then I will tell the name. 58 is called cerium, CE. 59 is called praseodymium, PR. Praseodymium. 59. 60 is called ND, capital N, small d. First letter is capital, second letter is small. Then 60, atomic number 60 is ND, means neodymium. 61, that is a promethium, PM. 59 I told that was the praseodymium, PR, and here it is a 61 is promethium. Okay, and 60 is neodymium, and 62 SM means samarium, and 63 europium, EU, europium, and 64 GD, gadolinium, and 65 terbium, TB, capital T, small b, terbium. 66, that is the DY, dysprosium, DY, 66, and 67 HO means holmium, and 68 is ER means erbium. 69 is thulium, TM, thulium, and 70 is YB, ytterbium, and 71 is lutetium, LU, lutetium. This is called lanthanide series, and means elements of lanthanide series. Now I want to tell you about this actinide series. Actinide is name of the elements of actinide series. Then 89 onward up to 103 I want to tell you. Then 90 is thorium, Th. 91 is protactinium. Protactinium means Pr, not it will Pa, protactinium, Pa. And 92 is uranium, U. 93 is Np, neptunium, Np. 94 is plutonium, Pu. 95 is americum, Am. 96 is curium, Cm. Cm means curium. 97 berkelium, Bk. 98 californium, Cf, californium. 99 Es, einsteinium, 99 in the name of Einstein, einsteinium. And 100 Fm, fermium, it is also name of scientist. And 101 mendelevium, Md, also name of scientist. 102 novelium, No. 103 lawrencium, Lr. Then this I have told you about the this actinium series or actinide series, lanthanum series or lanthanide series. Okay. Now I want to tell you about this physical properties of transition elements. Physical properties. Last class I have discussed about general things or introduction, also you can tell, of transition elements, means D block elements. Okay. Now I want to tell you about the physical properties. Okay. General properties of the transition element, means D block elements. Physical properties. Nearly all the transition elements display typical metallic properties such as high tensile strength, ductility, malleability, high thermal and electrical conductivity, and metallic luster. With the exception of Zn, cadmium, Hg, and Mn, they have one or more typical metallic structure at normal temperature. Again I am telling you, question is asked with this exception is Zn, cadmium, Hg, and Mn. Other have one or more typical metallic structure at normal temperature. These four elements are in exception. Okay, Zn, cadmium, Hg, Mn. And that Hg, you should know, it is the liquid. It is the liquid element. Okay. Now, lattice structure of transition metals, I want to tell you. Scandium actually it has HCP. First we know the name of this, already I discussed the previous classes, meaning of HCP, BCC, CCP. Okay. BCC means body centered cubic lattice. BCC, body centered cubic lattice. HCP means hexagonal close packed. HCP, hexagonal close packed lattice. Hexagonal close packed lattice. And CCP means cubic close packed lattice. CCP. C means cubic. Another C, close. P means packed. Then CCP means cubic close packed. Okay. And X, I will use the term X. it means a typical metal structure. Then now I am telling about the lattice structure of transition metals. First, I will tell about the SC, scandium. Scandium. Its structure is, it is found in a HCP structure. HCP, hexagonal close packed lattice. And also you can tell BCC. Titanium is also, its lattice structure is HCP. V is vanadium. It is a BCC, body centered cubic lattice. Chromium again BCC, and also it is found in CCP. Manganese Mn, that is just like a you can say a typical metal. Okay, it is a typical metal, manganese. And iron Fe, that is a BCC, body centered cubic, also exists in HCP. And cobalt is CCP, cubic close packed lattice. And nickel again CCP, copper again CCP, and Zn is X. X means a typical metal structure. Then manganese and Zn, I told you, it is a typical metal structure. Okay, and others I told the name of structure. This is the first series. Now second series, Y, yttrium. Y is called yttrium. It is also HCP or BCC lattice. Zirconium again same way, HCP or BCC lattice. Okay, lattice structure. And NB is BCC lattice structure. Molybdenum is also BCC lattice structure. And TC, technetium, that is a HCP. HCP. Ruthenium is HCP. And rhodium RH. Ruthenium is RU. HCP, and rhodium RH, that is the CCP. And palladium means PD, that is the CCP lattice structure. And silver is again CCP lattice structure. And cadmium is, that is the typical metal structure. Then 3 is the typical metal structure. First, manganese is a typical metal structure. Zinc is also a typical metal structure. And X is also a typical metal structure. And now third series I am telling you, that is the lanthanum. Then lanthanum is also HCP. All three structure you can tell, HCP, CCP, BCC. And next is hafnium, HF, that is a HCP structure or BCC structure, lattice structure. TA is tantalum, BCC structure. W is tungsten, BCC structure. RE, rhenium, HCP structure. OS, osmium, that is again HCP structure. IR, iridium, IR, again it is a CCP structure. PT means platinum, again it is a CCP structure. AU means gold, that is again CCP structure. And Hg means mercury, this is also a typical metal structure. Then typical metal structure is a manganese, Zn, cadmium and mercury. Okay, then actually sometimes in tough examination this question is asked about the lattice structure of transition metal. Now I am going little details. The transition metals, with the exception of Zn, cadmium and Hg, three metals are in exception. The transition metals, with the exception of zinc, cadmium and mercury, are very much hard. Okay, these three are exception, Zn, Cd and Hg. Others I am talking about, others are very much hard and have low volatility. Their melting and boiling points are high, and by graph also I will try to send this one, this is there graph, I will try to send. Then here by graph also, that is the melting point versus atomic number. Melting point, that is in Kelvin, 10 to the power 3 Kelvin is a very high melting point. 10 to the power 3 means 1000 Kelvin onward, I am telling you, melting point. 1000 Kelvin onward. Then melting point versus atomic number is there. Then you will find that three series are there. Then here this titanium, vanadium, chromium, manganese, ferrous, cobalt, palladium, nickel means first series. First series they have low melting point than second series, means zirconium, niobium, molybdenum, technetium, ruthenium, rhodium and auric. These are more, they have more melting point than first series, and this third series has highest melting point, means third series means HF, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, curium. Then tungsten is highest in third series. Tungsten is highest, and before tungsten tantalum is there, and before tantalum HF is there, and means HF is less, tantalum is more, W is highest, and again after that rhenium is less than tungsten, and osmium is again less than rhenium, and iridium is again less than osmium, and platinum is less than iridium. Okay, and after that AU, that is the list, you can tell, list, very soft. Gold is called soft metal. And in second, actually here in second I want to tell you, in second again molybdenum is highest. In second series molybdenum is highest melting point, and before that niobium is there, and before niobium zirconium is there, and TC it is less than MO, or less, and after that ruthenium is more than TC, and rhodium is again less than RH, rhodium is less than RU, ruthenium, and again silver is list in second series, and in first series which one is highest, then chromium, and which one is least, then Mn, manganese. Okay, and titanium is little high, vanadium is more than titanium, and chromium is highest, manganese is least, and after that ferrous, cobalt, nickel. Ferrous, cobalt, nickel, all are almost same. Okay, ferrous is little more, cobalt is little less, nickel is further less, but difference is less. And this copper is again less than copper is less than manganese, or little less, not more. Okay, then this I have told about the the melting point. Melting point melting points of the 3D, 4D and 5D transition metals I have now told you. 3D means first series and 4D means second series, 5D means third series. Okay. The high melting points of these metals are attributed to the involvement of greater number of electrons from n-1d in addition to the ns electron in the interatomic metallic bonding. Here you have to understand, high melting points of these metals are due to the involvement of greater number of electrons from n-1d in addition to the ns electron, means both n-1d electron and ns electrons are taking part in interatomic metallic bonding. That's why melting point is high. This question is asked. In any row, the melting points of these metals rise to a maximum of D5. Okay. In any row, melting points of these metals rise to a maximum at D5 except for anomalous values of Mn and Tc and fall regularly as the atomic number increases. They have high enthalpies of atomization. This I have told you that they have high enthalpies of atomization. The maxima at about the middle of each series. Maximum I am talking about that they have high enthalpies of atomization. The maxima means maximum at about the middle of each series. This indicates that one unpaired electron per d orbital is particularly favorable for a strong interatomic interaction. Okay, here reasoning I am telling you, the maximum will be at the middle of each series, and this indicates that one unpaired electron per d orbital is particularly favorable for a strong interatomic interaction. In general, greater the number of valence electrons, stronger is the resultant bonding. You remember in transition metals. In general, greater the number of valence electrons, stronger is the resultant bonding. Since the enthalpy of atomization is an important factor in determining the standard electrode potential of a metal, metals with very high enthalpy of atomization, means very high boiling point, tend to be noble in their reaction. Okay, you remember that metals with very high enthalpy of atomization, means very high boiling point, tend to be noble in their reaction. Okay. Now another generalization I told about the atomization. Now, another generalization that we can tell that the metals of the second and third series, metals of the second and third series have greater enthalpies of atomization than the corresponding elements of first series. Okay. Metals of the second and third series have greater enthalpies of atomization than the corresponding elements of the first series. This is an important factor in accounting for the occurrence of much more frequent metal-metal bonding in compounds of heavy transition metals. Okay, this is important things. Again, I want to repeat it. That metals of the second and third series have greater enthalpies of atomization than the corresponding elements of the first series. This is an important factor in accounting the occurrence of much more frequent metal-metal bonding in compounds of the heavy transition metals. Okay. Here also this you can study by the graph also. Graph is this kilojoule H, you can say H means enthalpy. I am talking about the enthalpy versus atomic number. Enthalpy versus atomic number, enthalpy of atomization. Enthalpy of atomization versus atomic number. Then you will find this nature of this things graph you can study, and this atomization in the what I discussed in the middle of the metal, they have low. Middle it will increase, but lowest atomization energy is in the almost middle of all transition metals, all three series. Fourth one is incomplete. You know all the things. Now I want to tell about the variation in atomic and ionic series of transition metals. Atomic and ionic size, variation in atomic and ionic size of transition metals. Why they are big or small? What is the variation? About that I want to discuss. Variation in atomic and ionic size of transition metals. In general, ions of the same charge, remember, in general, ions of the same charge in a given series show progressive decrease in radius with increasing atomic number. This is important things. Okay, question is asked. Ions of the same charge. Okay, in general I am talking about ions of the same charge in a given series show progressive decrease in radius with increasing atomic number. Radius decreases with atomic number. This is because, why this happens? This is because the new electron enters a d orbital each time. Okay, this is because the new electron enters a d orbital each time the nuclear charges increases by unity. If one electron will enter in d, then one can say this nuclear charge will increase by unity. Then always electron will enter to the d orbital, and always charge on nuclear will increase by unity. It may be recalled that the shielding effect, it may be recalled that the shielding effect of d electron, shielding effect of d electron is not that effective. Hence, the net electrostatic attraction between the nuclear charge and the outermost electron increases and the ionic radius decreases. Okay, this is the main reason. Okay, that d electrons always electron will enter to the d until it fills completely. Then shielding effect will be less. Then among themselves, that is the nucleus and these d electrons, they will attract. Nucleus will attract these electrons, and that's why size will be less. Okay. The same trend is observed in the atomic radii of a given series. Same things in all three series. However, the variation within a series is quite small. The variation is there, but variation is small. An interesting point emerges when atomic sizes of one series are compared with those of the corresponding elements in other series. The curves, already I said in this, I discussed about the graph, that there actually curve is there. The curve show an increase from the first means 3D to the second 4D series of the elements, but the radii of the 5D series are virtually the same as those of corresponding member of second series. This is very, very important point. Again, I want to tell you, the curve shows an increase from the first 3D, first means 3D to the second means 4D series. Okay, curve shows an increase from first to the second series of the element, but the radii of the third series are virtually the same as those of corresponding member of second series. This phenomenon is associated with the intervention of the 4f orbitals. This phenomena is associated with the intervention of the 4f orbitals, which must be filled before the 5D series of elements begin. Correct? This before 5D 4f must be filled. Then what will happen here? All electron will go to the 4f, and same thing will happen. That is, the shielding effect will be not proper and nucleus will attract. Then size will decrease. But same case, 5D is also there. 5D is also there. Then it will compensate, because 5f due to the 5f now it will decrease. With this 4f it will decrease. 5D is also there, that is somewhat bigger 5D. Then here what will happen, that due to this intervention of 4f orbitals, which must be filled before the 5D series of elements begin. Okay, that's why it will be as it is, as second, just like a second series. What is their size? Then third series size will be almost same. Third and second will be almost same. correct? Then here, because little variation was there, but now 4F has come. Then what was increasing, now it will decrease due to 4F. 4F, then it will become just like almost same as second. See, second was more than first. First series, elements of size of the elements of second was more than first series. But now third, actually it was expected more. But now problem has come here that 4F started. Then now electron just began to go to the 4F, and without filling up the 4F, it will not go to the 5D. And 4F, same thing will happen. It will be, these electrons will be attracted towards nucleus. Then size will decrease. Then now due to that, now it will be just like same as a group 2, series second size, almost same, because it was expected more due to the 5D, but 4F started. Then what was the increase? Now it is compensated by this thing, decreased by 4F. That's why it became almost same size. And this actually, this has due to this, it has created a special actually effect. This phenomena is associated with the intervention of the 4F orbitals, which must be filled before the 5D series of the elements begin. The filling of 4F before 5D orbitals results in a regular decrease in atomic radii called lengthanoid contraction. Question is asked, lengthanoid, LANTHANOID, lengthanoid contraction means it will decrease. Okay, size will decrease, which essentially compensates for the expected increase. Decrease compensated to the expected increase. That's why it became same. One side it was trying to increase, but other side wanted to decrease. That's why it became almost same. Okay, and size. And this actually question is asked, what is the lengthanoid series? Okay, this question is asked, lengthanoid contraction. What is the lengthanoid contraction? Always question is asked. Then again I want to tell you, the filling of 4F before 5D orbitals result in a regular decrease in atomic radii called lengthanoid contraction, which essentially compensates for the expected increase in atomic size with increasing atomic number. The net result of the lengthanoid contraction is that the second and the third D series exhibit similar radii. Effect of lengthanoid contraction is that the second and the third series exhibit similar radii. Means zirconium, as for example 116 picometer PM, and HF, that is the third, this is a 159 picometer. Then see the differences, 160 and 159 picometer, almost same, and have very similar physical and chemical properties. Okay, second and third series have very similar physical and chemical properties, much more than the expected on the basis of usual family relationship. Okay, this is an important point I have discussed. Now furthermore I want to tell you the factor responsible for the lengthanoid contraction. What are the factors? The factor, what is the factor actually, that I am telling you, why does it happen? Already discussed main things. The factor responsible for the lengthanoid contraction is somewhat similar to that observed in an ordinary transition series and is attributed to similar cause, that is the imperfect shielding. Imperfect shielding of one electron by another in the same set of orbitals. Means electrons are going in the same orbital, but they are not shielding properly. That is called the imperfect shielding of one electron by another in the same set of orbitals. However, the shielding of one 4f electron by another is less than that of one d electrons by another. Okay, there it was more. In d electron we are shielding more, but in 4f it is less. And as the nuclear charges increases along the series, there is a fairly regular decrease in the size of entire 4fn, a small n orbitals. 4fn maybe n may be 1, 2, 3, 4 up to and 10. That's why size decreases. Decrease in the size of entire 4fn orbitals. The decrease in metallic radius coupled with increase in atomic mass. Again important point, question is asked. The decrease in metallic radius, you have seen radius has decreased. The decrease in metallic radius coupled with increase in atomic mass, but mass is increasing and size is decreasing, radius is decreasing, results in general increase in density of these elements. Density will increase in these elements. Thus, from titanium, means titanium is 22 atomic number, to copper is 29. The significant increase in the density may be noted. Okay, and here again by graph or by curve you can understand. Okay, that is the trend in atomic radius of transition elements. Then here you will find that scandium, you can tell first series, their radius is more than second series. This first series, scandium, titanium, vanadium, chromium, manganese, ferrous, cobalt, nickel, copper, zn. Its radius is more than second one. Second one means second series: yttrium, zirconium, niobium, molybdenum, technetium, and ruthenium, rhodium, palladium, agriculture, cadmium. Okay, then first one is more, radius is more than second one, and third one series, that is the lanthanum, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, auric, Hg. It is less, little less. Okay, little less, or you can tell almost same, but you can tell little less only. Then this radius, it is in nanometer, Then this I have discussed about the, you can say, melting point, and main thing that lanthanide contraction, and also why factors, why it happens, and density, why it increases, that also I have discussed. Okay, now this electronic configuration, already I have discussed electronic configuration, enthalpy of atomization, all things I have discussed. Metallic and ionic radii, all things I have discussed. Okay, now I want to discuss ionization enthalpies. Then just like ionization energy, ionization in energy, that is called ionization enthalpy. Then what I have discussed in other elements, here in transition elements also same thing will happen, that how easily you can remove the electron from the metal and how it is difficult to remove the electron. If it is easy to remove the electron, then less energy will be required to remove the electron from the outermost. If you can say it is if the size is small, then nuclear will attract the electron, correct? Then it is difficult to remove the electron. That time higher energy will be, more energy will be required. The concept is here also same. Okay. Now I will tell a little more. Due to an increase in nuclear charge, which accompanies the filling of the inner d orbitals, there is an increase in ionization enthalpy along each series of the transition elements from left to right. This is the very important. Due to an increase in nuclear charge, which accompanies the filling, due to the filling in nuclear charge increased. Okay, due to an increase in nuclear charge which accompanies the filling of the inner d orbitals, there is an increase in ionization enthalpy along each series of transition elements from left to right. Okay. However, many small variations occur. Okay. The values of the first three ionization enthalpy that you know, if one electron you will remove, that is the first ionization. If second electron you will remove from the outermost, then it is called second. If third, then third ionization. Then you know first it is easy to remove first electron, and it is little difficult to remove second electron, and most difficult to remove third electron. That's why for the third more energy is required. Means ionization energy, means ionization enthalpy will be more for third and less for second and very less for first one. This is a general can say this thing, reason, cause. Okay. Then this if you will see the value, then you will find all the things. The values for the first three ionization enthalpies of the first row elements. Okay. These values show that the successive enthalpies of these elements do not increase as steeply as in the main group elements. Means other than transition elements, there also increases, but not so much like these things, transition elements. Although the first ionization enthalpy in general increases, the magnitude of the increase in the second. Although the first ionization enthalpy in general increases, the magnitude of the increase in the second and third ionization enthalpies for the successive elements in general is much higher. Okay, means second and third is much higher in comparison to the first. The irregular trend, sometimes irregularity will be there. The irregular trend in the first ionization enthalpy of 3D metals, though of the little chemical significance, can be accounted for by considering that removal of one electron alters the relative energy of 4s and 3D. Here it should understand the irregular trend in the first ionization enthalpy of the 3D metals, though of little chemical significance, can be accounted for by considering that the removal of one electron alters the relative energies of 4s and 3d orbitals. So the unipositive ions have Dn configuration with no 4s electrons. Okay, unipositive ions have Dn energy accompanying ionization with some gains in exchange energy. Here again you have to understand, unipositive ions have Dn configuration with no 4s electron, because s electron it will go outside as ionization. Okay, hence there will be no s electron. There is thus a reorganization energy. Here you should understand again, because s electron is removed, then there will be no s orbital. Then there is thus a reorganization energy. Again all electron will reorganize. That is called reorganization energy accompanying ionization with some gain in exchange energy. Okay, reorganization gives some gains in exchange energy as the number of electrons increases and from the transference of s electron into d orbitals. I told you that from the s electron may come to the d orbitals. That's why it is called exchange energy, or also you can tell reorganization energy. Then there is the generally expected increasing trend in the value as the effective nuclear charge increases. Okay, it is expected increasing trend in the values as the effective nuclear charge increases. However, the value of chromium is lower because of the absence of any change in the D configuration. Chromium is a lower. Value of chromium is lower, means ionization energy value. Chromium is lower because of the absence of any change in the D configuration, and the value for Zn higher because it represents an ionization. Zn is a higher ionization energy because Zn I told you is higher because it represents an ionization from the 4s level. The lowest common oxidation state of these metal is +2. Generally, transition metals will have a common oxidation state of +2. Others are also there, but +2 is common. To form the M2 plus, M means metal, M2 plus ions from the gaseous atoms, the sum of the first and second ionization energy is required in addition to the enthalpy of atomization for each element. Again you listen, the lowest common oxidation state of these metal is +2. To form the M2 plus ions from the gaseous atom, the sum of the first and second ionization energy is required in addition to the enthalpy of atomization for each element. Means both are considered, first and second ionization but plus enthalpy of atomization. The dominant term is the second ionization enthalpy, which shows usually high value for chromium and copper, where the DF and D10 configuration of the M plus ions are disrupted. Chromium, you know that it is a D5, and copper is D10. It is a stable configuration of the M plus and M plus 1 plus M plus ions are disrupted with considerable loss of exchange energy. The value for Zn is correspondingly low. This value for Zn is low as the ionization consists of the removal of an electron, which allow the production of the stable D10. Okay, Zn is less low. This ionization energy for Zn is low as the ionization consists of the removal of an electron, which allow the production of the stable D10. That's why it is low. D10 configuration. The trend in the third ionization energy. The trend in the third ionization enthalpy is not complicated by the force or vital factors, and so the greater difficulty of removing an electron from the D5 and D10. D5 means manganese first group, and D10 means Zn, then Mn2 plus and Zn2 plus. Okay, this Mn D5 and D10 ions superimposed upon the general increasing trend in general. Again, you listen, the trend in the third ionization enthalpy is not complicated by the force or vital factor, and so the greater difficulty of removing an electron from the D5 and D10, because both are stable, hence it is very difficult to remove the electron from D5 and D10. Because first and second, S has 2 electron maximum, then first ionization, second ionization somewhat easy. But now after removing first and second, for the third it should go from the D. But D5 and D10, manganese and Zn, is very difficult. Okay, or greater difficulty, okay, or vital, and shows the greater difficulty to removing an electron from the D5 and D10 ions superimposed upon the general increasing trend. In general, the third ionization enthalpies are quite high, and there is a marked break between the value of Mn and Fe. Manganese and ferrous ion. Ferrous is less, manganese is more. Also, the high values for copper, nickel, and Zn indicate why it is difficult to obtain oxidation state greater than 2 for these elements. All have D. It is difficult to remove from the electron from the d orbitals. That's why copper, nickel and zinc indicate why it is difficult to obtain oxidation state greater than 2 for these elements. Although ionization enthalpy gives some guidance concerning the relative stabilities of oxidation state, this problem is very complex and not, you can say, amenable to ready generalization. Okay, it is a helpful. Ionization enthalpy is just like simply guidelines, some guidelines concerning the why it is stable, relative stability of oxidation state. Only it is guidelines, not exact. Then today I am stopping only here. Next class I will discuss oxidation states in details. Okay, thank you.